Okay, hello everyone and welcome to today's 1W-MINDS talk. Today's speaker is Ron Levie, senior lecturer at Technion. He did his PhD at Tel Aviv University and has been in Berlin and München before joining Technion. His research includes applied harmonic analysis, randomized algorithms, and not the least deep learning. And this is the theme of today's talk. It's titled Regularity of Graph Neural Networks. So the floor is yours, Ron.
Yeah, thank you, Axel, for the introduction and the invitation. So I'm going to talk about the regularity of graph neural networks. So what I'm going to do is I'm going to introduce a structure on the input space of graph neural networks that reveals that graph neural networks behave regularly. And from this, we are going to derive as corollaries generalization theorems and universal approximation and more theoretical results. Okay, so the different parts of this talk are from works with my different collaborators. Okay, so you know that often the data is not given to us as points in a Euclidean space like images or audio signals, but it's given as graphs. And this is why graph neural networks are very popular and very successful both in the academy and the industry. So for example, you can represent molecules as graphs where the nodes represent atoms and the chemical bonds are the edges, and then you can do some different predictions. For example, you want to classify if a molecule is antibacterial or not, right? So companies discover drugs like this, they use a graph neural network to do pre-screening. You can represent a social network as a graph where nodes are people and the edges are social interactions like friendship, and then you can do various predictions on the nodes, right? And the data is a graph, and each node comes with a feature. Okay, surfaces, you can represent them as graphs, and you can do surface classification, recommendation systems, right? So many companies use graph neural networks. Google Maps are using graph neural networks to do traffic prediction, and so on. And in my research, I developed mathematical foundations of graph neural networks, and then I also use these foundations to derive applications. So if we compare the analysis of graph neural networks to the case of more standard neural networks like convolution networks or multi-layer perceptrons, so standard neural networks are mappings from vector spaces to vector spaces, right? So the dimension is fixed in the input and the output space. And the fact that we have a regular structure, a Euclidean structure, allows us to prove various theoretical results like universal approximation theorems that show that any continuous function can be approximated by a neural network, and generalization theorems that show us that if we train a network on the training set, we are guaranteed that the performance on the test set is close to the performance on the training set. Okay, so to prove such results, you typically need to use the structure of the input and output space, the metric space properties. So for example, you use compactness, covering number, how many balls of a certain radius you need to use to cover the whole space. You use continuity of functions and so on. Now, if you compare to the situation of graph neural networks, here the situation is a bit less clear, because a graph neural network is a function that takes a graph with node features, namely a graph signal. So for us, a signal is a mapping from the nodes, from the set of nodes to features in some Euclidean space. So a graph neural network takes a graph signals and returns either another signal on the same graph or one feature for the whole graph signal. Now, the challenge is that it's not clear how to define a metric on the input space, right? A metric that allows us to compute the distance between any pair of graph signals. So there are some works in the past that define metrics to derive theorems. One approach, for example, is you can fix the number of nodes and take the adjacency matrix and now treat it as a point in a Euclidean space because the dimension is fixed. This is related to edit distance, and then you can try to prove things. But this metric is not so natural because, in a sense, it is too fine. The topology that this metric gives is too fine. There are graphs in nature that we would expect to be close to each other because, in some sense, they represent the same phenomenon, but they are far apart in this metric. And then it's more difficult to be compact if you don't upper bound the number of nodes and so on. So our goal is to construct a metric on the space of whole graph signals that has the following properties. So first of all, it should give a meaningful notion of graph signal similarity, namely graph signals that intuitively represent the same phenomenon they should be close to each other. And we should be able to compare any two graphs of any size, of any number of nodes, of different number of nodes, right? And also the metric should have nice properties that allow us to do analysis. So first of all, we are going to construct a metric that gives a compact space. And secondly, the message passing networks, graph neural networks, are going to be Lipschitz continuous over this metric space. And these two properties together allow us to prove generalization theorem, universal approximations, and more. Now, if you think about it, these are two competing requirements, requiring that, so the space of functions, the space of message passing networks is given to me. I'm not designing the functions with respect to the metric that I designed, right? The functions are given. These are the message passing networks that engineers use to solve various problems. This is a space which is given to me. Now, if I want my space to be compact, it means that in some sense, all of the points in the space should be close to each other. And then the more close to each other the points are, the more difficult it is to be continuous because maybe now message passing networks are going to have jump discontinuities, quote unquote. Okay, but still we are able to construct such a metric which is both compact and message passing networks are Lipschitz continuous. Okay, so first of all, I want to explain what message passing networks are. So this is probably the most popular type of graph neural network. Most of the practical examples of graph neural networks are special cases of message passing networks or slight extensions. So in a message passing network, the input is a graph with node features. Let's represent the node features with different colors. So these are just values in some vector space. And what we do in each layer of the network, we want to update the value of each node with respect to the values of its neighbors. So suppose we want to update the value of this node in the next layer. So we consider a trainable function called the message function. For example, this can be a multi-layer perceptron that takes the feature value of the central node that I update and the feature value of the neighbor. And I use this message function on all of the neighbors. And I think about the values that are computed as messages sent from the neighbors to the central node. And then the central node looks at all of the messages and aggregate them to one value. So you can, for example, average all of the messages, sum them, or take the max. As long as the operation is invariant to permutation, because there is no natural ordering of edges, right? Okay, and so you have the aggregated message, and then you plug this value in another function, which is called the update function that takes the previous value of the feature of the central node and the aggregated messages, and this is going to be the value of the node in the next layer. Okay, so phi and psi are trainable, and they use the same psi on all of the nodes. So this is why, in a sense, you can think about it as some sort of non-linear convolution, because somehow you have the same template that you use in all neighborhoods of the graph. And different layers have different trainable message and update functions. And then, let's say at the end, you want to do graph classification. So then you need to do global pooling. You average all of the features of the nodes, or you take the max, or something like that, and this is going to be the output. So we are going to focus on normalized sum aggregation. So we sum all of the messages, and we divide by the total size of by the degree of the graph, right? The number of nodes. So the two most popular approaches to aggregation are sum aggregation and max aggregation. And normalized sum aggregation gives similar results, similar accuracy to sum aggregation. And this is the aggregation we are going to focus in our theory. Okay, so we want to design a metric between graph signals. And the metric is going to have the following interpretation. Two graph signals are going to be close to each other if and only if they look like they were sampled from the same stochastic block model. So what is a stochastic block model? This is a generative model of graphs where you consider a set of classes and probabilities of having edges between each pair of classes. And then you randomly sample a graph from the stochastic block model by randomly sampling nodes from the different clusters and connecting each pair of nodes according to the probability that comes from the stochastic block model. Okay, so you can sample graphs of different sizes. And the graph that you sample is a random variable because the edges are Bernoulli variables. Okay, so in this picture, I can tell you these are two random graphs that were sampled from the stochastic block model. But because it's only a drawing, I can also tell you these are actually two deterministic graphs. And in some sense, they look like they were randomly sampled from the stochastic block model, even though they are deterministic. In the sense that if you look at the edge densities between pairs of sets of nodes, they behave like the expected value, expected number of edges from the stochastic block model. Okay, so then you can ask yourself the following question. Given a deterministic graph, is it always possible to find a stochastic block model such that the graph looks like it was randomly sampled from the stochastic block model, even though the graph is deterministic? And the answer to this question is yes. This is called Szemerédi regularity lemma. The lemma says that for any deterministic graph, it's always possible to find a partitioning of the nodes to classes such that the densities of edges between pairs of node sets behave like the expected number of edges if the graph was random. So I'm going to give you an exact definition in a second. The nice thing about this lemma is that the number of classes doesn't depend at all on the graph itself. It doesn't depend even on the number of nodes. The number of classes only depends on how much I want the graph to look random. So Szemerédi proved this lemma in 75 for bipartite graphs, and then he extended the proof in 78 for general graphs. And there are many extensions and many proof techniques and many variants of the regularity lemma. For example, Noga alone proved the first gave the first algorithmic proof, an algorithm that computes the communities in polynomial time. And the lemma has, you can prove different theorems in graph theory and number theory using the regularity lemma. Okay, so I want to walk you through one variant of the regularity lemma, which is called the weak regularity lemma. It was proven in 1999 by Fritz and Cannon. I think it's a nice lemma, so I think it's also important for the construction of the metric. So let me walk you through all of the definitions in detail. So we have a deterministic graph, and we want to take the nodes and partition them to sets in such a way that somehow the statistics of edges, the density of edges look like the statistics if the graph was random. So we need some definitions of counting edges between sets of nodes. So let's denote the node set by V. And for each pair of sets of nodes, U and S, let's denote by EGUS the number of edges in the graph G between nodes in U and nodes in S. Now, if somebody gave me a partition of the nodes to disjoint sets, V1 until Vk, there is a way to find the stochastic block model that best approximates the graph based on this partition. Okay, so the probability of having an edge between the class Vi and class Vj would be the number of edges in the graph between Vi and Vj divided by the maximal possible number of edges between the two sets. Vi, the size of Vi times the size of Vj. So this would be the best stochastic block model to approximate the graph if I fixed the classes. Now the graph is deterministic, but if the graph was random, I could have computed the expected number of edges between any pair of sets. So this is the formula, right? So if the graph was random, then for every set of nodes U and set S, the expected number of edges could be computed as follows. I go over all of the pair of classes, namely all of the blocks. I count how many nodes in U I have in class Vi, how many blocks in S I have in class Vj, and multiply it by the probability of having an edge between these two blocks, between these two classes, and sum over all of the classes. So if the graph was random, this would have been the expected number of edges, and this gives me a way to assess how much the graph looks random, because I can compare the actual number of edges between U and S to the expected number of edges. And this is called irregularity. So given a fixed partition of the node set, the irregularity is the maximum over the pair of node sets of the difference between the actual number of edges between U and S and the expected number of edges if the graph was random. Okay, so the higher the irregularity, the less the graph looked like it was randomly sampled from the stochastic block model. And now the weak regularity lemma says that there is always a way to find the sets Vj such that the irregularity is small. Okay, for every epsilon, which is a bound on the irregularity, and every graph, there is a partition of the nodes to non-intersecting sets, where the number of sets only depends on how much I want the irregularity to be small. It doesn't depend on the size of the graph or on any other property of the graph, right? So there is a partition such that the irregularity is small. Okay, so in summary, one way to interpret this lemma is that even though large deterministic graph may look complicated, they're actually regular and behave as if they were randomly sampled from a stochastic block model where the number of blocks doesn't depend on the size of the graph. It only depends on how much I want the graph to look random. Okay, so we want to build a metric based on the notion of irregularity, but we need a couple of extensions. So first of all, the regularity lemma is for graphs, but the input space of message passing networks are graphs with node features, graph signals. So we want to extend the lemma to graph signal. So, and the second extension is, so we are going to build a metric, and the metric space, the space of graph signals, is not going to be complete under this metric. And then we want to take the completion because we want to end up with a compact space. And to take the completion, we need to take limit objects of graphs, and these are graphs with continuous node sets. So let me tell you a little bit about graphs with continuous node sets. So these are called graphons. A graphon is a graph where the node set is the interval 0 to 1. Okay, you have a continuum of nodes. And the graphon is a measurable function between pairs of nodes in 0 to 1 to 0 to 1. So Wxy is interpreted as the edge weight between node X and node Y, or the probability of having an edge between X and Y. Now, we treat the interval 0, 1 only as a measure space, not as a topological or metric space. And because we only treat it as a measure space, graphon theory is a theory about measurable functions, not continuous functions, or smooth functions or Lipschitz functions. And now, because we only treat measure properties, 0, 1 is quite a general space. It is the standard atomless probability space. So it is equivalent to 0 to 1 to any dimension and to any Polish space, right? Any compact manifold and so on. So this is not working with the node set 0 to 1 is not a restriction. It's quite generic. Okay, now you can also interpret graphons as generative models of graphs. In some sense, they're like extensions of stochastic block models. To sample a graph from a graphon, you sample uniformly and independently nodes from the node set 0 to 1, and then you connect each pair of nodes according to the probability Wx and Xn, right? According to the graphon weight. Okay, so you can embed the space of graphs in the space of graphons. So in some sense, graphs are special cases of graphons. You do it by taking the adjacency matrix of the graph and extending it as a piecewise constant graphon. Okay, so we think about piecewise constant graphons as graphs. So anything we prove for graphons is going to be immediately true for graphs as a special case. Okay, so there is a way now to extend the regularity lemma to graphons. So Lovas and Szegedy did it in 2007. And turns out that in the case of graphons, irregularity becomes a norm. And it's a norm which is called the cut norm. So if we have two graphons, W1, W2, the cut norm of the difference between the two graphons is defined as follows. You go over all of the pairs of node sets in 0 to 1. You compute the average edge weight of the first graphon minus the average edge weight of the second graphon, absolute value outside, take the supermum, and this is cut distance. So in some sense, the cut norm is the block. The cut norm of the difference between W1 and W2 is the block in which the edge densities behave the most differently. And then you take this difference. This is the cut norm. Okay, so for us, we work with graph signals. So they are going to be extended to graphon signals. So now a signal is a mapping from the node set 0 to 1 to R or to some RD, but for simplicity, let's restrict the analysis to R. And we define the graphon signal cut norm in our situation of the difference between two graphon signal pairs as the sum of the cut norm between the two graphons and the definition of cut norm for the signals. Okay, so we define the cut norm of the difference of the signals as a supermum over the set of nodes such that the average value of the first signal minus the average value of the second signal is maximized. Now, the cut norm of graphons is not equivalent to any LP norm, but the cut norm of signals is equivalent to the L1 norm. So it's bounded by the L1 norm from above and from below by 0.5, the L1 norm. So in the whole analysis, you could replace this part by the L1 norm, but the proofs are easier when you directly work with the cut norm, and also the bounds are going to be nicer using this norm. Okay, so the last thing I want to do here is, because I'm interested in graphs, and the graphs don't have a natural ordering of the nodes, I want the whole analysis to be up to a permutation of the indices, okay, up to re-indexing the graph. So we want to define a permutation invariant distance So we define the graphon signal cut distance between a pair of graphon signals as the cut norm of their difference up to the best permutation that aligns them the best possible way. Okay, now permutation, because the node set is now a measure space, permutation is modeled as a measure preserving bijection. It's a one-to-one mapping which is measurable, the inverse is measurable, and it preserves measures. This is how we think about permutation in the measure space case. And because we inherited this definition from irregularity, we also inherit the interpretation. So the interpretation of the cut distance between two graphon signals is, in a sense, how much these two graphon signals look like they were sampled from the same stochastic block model. Okay, so we have our metric, and now we are able to extend the regularity lemma to the case of graphon signals. So now this version of the regularity lemma says the following. For every graphon signal and every error tolerance, there exists a piecewise constant graphon signal, W prime F prime, namely a stochastic block model, on the equipartition into this many intervals, right? And the number of intervals only depends on the error tolerance, such that the cut distance between the graphon signal and the stochastic block model is bounded by epsilon. Okay, so the nice thing about this version of the theorem is that the partition, it's not only that the number of parts in the partition is fixed, but the partition itself is fixed. The partition is just the partition to intervals of the same length. Okay, because the whole analysis is up to permutation, I can always sort the sets, because they are non-intersecting, into intervals. And then you see that if you take the space of stochastic block model of this fixed block structure, it is actually a finite dimensional space. It is finite dimensional, so it means that we can, up to epsilon, we can approximate the space of all graphon signals by a finite dimensional space. And from this, you can prove that the space of graphon signals is compact. Okay, so before that, let me give an illustration of the theorem. Here we have a graphon signal. So the graphon is plotted in grayscale. This is 0, 1 square. And the signal is plotted on the diagonal in color. And the theorem says that there is always a permutation of the node set that brings the graphon signal to a representation which is close to a stochastic block model. Okay, so as I told you before, by the fact that we approximate the space of all graphon signals by a finite dimensional space, we can prove that the space of graphon signals is compact, and we can also bound the covering number. So for every epsilon, we know that we need this many balls of radius epsilon to cover the whole space. Okay, so if we go to the regularity lemma, this bound is essentially tight. Okay, you can show that by reducing this constant to a smaller constant, you can show that for every epsilon, there is a graphon signal such that there is no stochastic block model with less than this many blocks that approximates the graphon signal. So this regularity lemma is essentially tight up to this constant 2. But the covering number, I don't know if it's tight or not. This is still open. So I derived it by taking quantizing this finite dimensional space. So initially I thought this bound is essentially tight, but now I'm not sure anymore. So this is an open question, if it's essentially tight or not. Okay, so this is a nice result because we have the space of all graph signals, which looks like a huge space because graphs can be of any degree, right? Any size, any number of nodes and any topology. So it's definitely not finite dimensional. But still, we built a meaningful metric under which this space is small. It is dense in a compact space. The space of graph signals is dense in the space of graphon signals, which is compact. But all of this is not useful for us unless we show that message passing networks are Lipschitz continuous with respect to this metric. Right? Because in principle, I could have defined a very coarse metric. Right? I could have said that the distance between every pair of points is 0. Then we have a very trivial topology. Obviously, it is compact, but it is meaningless, and it doesn't describe the behavior of message passing network. They are not continuous. Okay, so the next thing we want to prove is that message passing networks are continuous with respect to this metric. And for that, we first need to extend the definition of message passing networks from graph signals to graphon signals, right? Because now we live in the complete space of graphon signals. Okay, so if you remember, in message passing networks, we have a message function that takes the feature at the node that I want to update and a feature of a neighbor. Now, this message function just takes a pair of features. It doesn't care if the node set is continuous or discrete. So here, there's nothing to extend. The only thing we need to extend is the aggregation. So instead of doing normalized sum aggregation, now we do integral aggregation. We look at all of the messages sent to X, and we integrate them against the edge weight that come from the graphon. And in a sense, this is the canonical definition because in case that the graphon is a piecewise constant graphon which is induced from a graph, then doing normalized sum aggregation on the graph is the same, and then inducing a graphon is the same as first inducing a graphon and then doing integral aggregation. Okay, so this is in a sense the canonical definition. Okay, and then I was able to prove that message passing networks are Lipschitz continuous in cut distance. So if you have, if you take two graphon signals and you plug them in a message passing network and you compute the cut distance of the output, this is bounded by the cut distance between the two graphon signals up to a constant which is guaranteed to exist. This is the Lipschitz constant of the message passing network. Now, the only thing I need to assume is that the message functions are Lipschitz continuous. And this is a very mild assumption, because if we want to be able to train the network, then the message functions should be differentiable. So obviously, it's very natural to assume that they are Lipschitz. And that's the only assumption you need. So this Lipschitz constant of the whole message passing network is a function of the Lipschitz constants of the message functions of all of the layers. Okay, and now from the fact that the domain is compact, the space of all graph signals or graphon signals is compact, and message passing neural network are Lipschitz continuous, these two things together allow us to prove various theoretical results, like a generalization theorem that says that if the if the empirical risk is small, we are guaranteed that also the statistical risk is small. So maybe let me give you a reminder from statistical learning, just to level the playing field, to make sure we understand what we're talking about. So we consider a situation, typically in statistical learning, where the data lives in some probability space, right? The data is sampled from some probability space. So for us, this is a probability space over the space of graphon signals. Right? It's a Borel probability space over the cut distance. And let's assume that for suppose we are doing classification, right? So for every graph signal, there is a ground truth label, a ground truth class, YX. And then we define a loss function that takes pairs of points from the output space and computes how close they are together. So if you plug in a graphon signal in my message passing network, I get something. Now there is also the ground truth. and the loss tells me how accurate my message passing network is specifically for this input, and then I average the loss on the whole data set. So this is the expected loss. It is called the risk, and the goal in learning is to minimize the risk, but we cannot minimize the risk because we don't have access to yx, and we don't have a way to compute the measure here. The measure only lives in theory. So what we do in practice, we only focus on data that was randomly independently sampled from the probability space, and we minimize instead the empirical risk, the average loss over the training data. Okay, and the goal in uniform generalization bounds is to bound the difference between the empirical risk and the statistical risk. In a sense, you can think about it as a sort of Monte Carlo approximation, but it's not really a Monte Carlo approximation because right, xj are randomly sampled, but theta, the neural network, depends on the samples because I train the network, I feed the network to the data. So it's not really Monte Carlo theory, and there is complication because when I take the supermoon here, right, if I fix theta, then it is a Monte Carlo approximation, but different thetas require different events in which the Monte Carlo approximation is a good approximation of the integral. And then I need to take the intersection of all of these events, and this complicates the analysis. Okay, anyway, we were able to prove that the difference between the empirical and statistical risk decays to zero as the training set, the number of points in the training set goes to infinity. So M here is the number of samples in the training set, and psi inverse is a function that decays to zero. It decays something like log. So it decays very, very slowly. But the nice thing about this theory is that we don't need any assumption on the data distribution. The distribution from which the data comes from can be anything. And also, we don't need any assumption on the message passing network. We don't need any assumption on the number of parameters. The only thing we need to assume is that the message function are Lipschitz, and we need to bound the number of layers. So if you compare our analysis to previous papers that analyze the generalization properties of graph neural networks, in all previous papers, you have special assumptions. You assume something about the graphs, bounded degree, stuff like that. And you also need assumptions on the message passing network. For example, messages are linear, or all of the message functions are shared across all of the layers. So you have only one message function, and so on. So they have much better bounds. So you can interpret our result as what happens if all of the assumptions from previous papers are not met in practice. And typically they're not met in practice because they're simplistic. So even if none of the assumptions are true, you're still guaranteed some convergence rate, even though it is slower. Okay, another application of this theory is a sampling theorem that says that if you have a graph and you subsample it randomly, you subsample the nodes randomly and consider the subgraph, then applying a message passing network on the small graph gives you a similar result to applying the message passing network on the large graph. And again, you don't need any assumptions whatsoever on the graph signal. It can be any graph signal of any size. Right? The decay obviously depends on the size of the small graph, but not of the large graph. So this justifies a practice that people do when they work with very large graphs. So, you know, companies like Google, Facebook, they work with graphs of hundreds of millions of nodes and 100 to 1,000 times the number of edges. And there's no way to fit all of this to memory. Okay, so you need to subsample the graph, and this theorem justifies the subsampling under no assumption on the data. Okay, so what we did until now is we showed that two graph signals are close to each other. If two graph signals are close to each other, then the outcome of any message passing network on the two graph signal is also going to be close. So now I want to prove an if and only if result. We want to prove that two graphs are close to each other if and only if the outcomes of the application of any message passing network on the two graphs are close to each other. And for this, we need to relax the metric. So if you remember, the cut norm, the cut distance was defined as the cut norm up to the best permutation. So up to the best hard alignment between the two graphons. And now we relax the hard alignment to a soft alignment, namely to a Markov operator. You can think about the Markov operator as taking the nodes and splitting them and mixing them together and then doing the alignment. Okay, so this, when you relax the permutation to Markov operator, the distance you get is called tree distance. Now, the analysis that we derive now is restricted to graphs with no node features. So only graphs with no signal. Okay, so in situations that you just have a graph, then you can prove that two graphs are close to each other if and only if the outcome of the application of any message passing network on the two graphs is also close to each other. So this is an expressivity result. It tells you something about the separation power of message passing network. And from this, we can derive a universal approximation theorem that says that any continuous function that takes graphs and return, or graphons and return numbers, which is continuous over tree distance, can be approximated by a message passing network. And in some sense, the tree distance gives the finest topology on which this is possible. If you take a finer topology, it means that the points are further apart, and then it is easier to be continuous. So you have too many continuous functions, and you can no longer approximate them with message passing networks. So in some sense, this universal approximation theorem is optimal. Okay, so what we discussed until now are theoretical results, which is nice, but I want to give you now a practical application which is inspired from the regularity lemma. So this is a paper called Approximately Equivariant Graph Networks. So here we have the following situation. The data set consists of one fixed graph and many signals on this graph. So one example setting is traffic prediction. Okay, so in traffic prediction, the graph is fixed. The graph represents the roads, and the roads don't change; they're fixed. And the signal is for each part of the road, how many cars there are in this part of the road. Okay, so the signal changes over time. You have many signals that you measured over time, but one graph. In such a situation, because the dimension is fixed, the graph is fixed, you can just treat the signals as points in a Euclidean space and train a multi-layer perceptron to do traffic prediction. But this is not going to work well because you're going to overfit. You have too many trainable parameters. And the typical approach to alleviate this problem in geometric deep learning is to consider neural network that respect the symmetries of the problem, that commute with the symmetries, and this is a way to reduce the number of trainable parameters. Now for us, because the domain is a graph, the natural symmetries are automorphisms. The problem is that automorphisms are very sensitive to perturbations. You can have a graph with a very rich symmetry group, but then if you delete only one edge from this graph, you completely ruin the symmetry group and you get a very small group with very trivial symmetries. And this is why graphing applications typically don't have interesting symmetries. They have a very small symmetry space because they are noisy phenomena that were sampled from some continuous phenomenon with noise. Okay, so this is not respecting the automorphisms of the graph is not going to help you reduce the number of parameters because you don't have enough symmetries. Now what we did is we said, okay, you can approximate the graph using a stochastic block model, and then you can consider the symmetries of the stochastic block model. And now you have many more symmetries because at least you have all of the permutations within each class. So you have a much bigger space of permutations. And you can show that these are approximate symmetries of the graph. So if you apply these permutations, the symmetries of the stochastic block model to the graph, the adjacency matrix changes, but not by much. And this is due to the regularity lemma. Okay, and then you can use representation theory to derive all of the linear layers that commute with these symmetries, and then use a multi-layer perceptron based on this limited space of linear layers. It has much less trainable parameters, and then the performance is very nice. It's improved. Okay, so in summary, what I showed you is that even though deterministic large graph signals may appear to be complicated and intricate, they're actually regular and behave like they were sampled from stochastic block models. From this observation, we can construct a metric, the graphon signal cut distance. And under this metric, the space of graphon signals is compact and message passing networks ellipsis continuous. And these two properties together allow us to prove generalization theorems, universal approximation, expressivity, sampling. Okay, so if you're interested in this line of work, you can take a look at my papers. Okay. Thank you.
Thank you very much for the very, very nice talk. Are there questions from the audience? Let me start with one. So in the final slide about the equivariant networks, so what you do here is that you take the graph and then you determine these neighborhoods, and then you consider the group of permutations within the neighborhood.
With semi-direct product of the group of symmetries of the stochastic block model. The stochastic block model itself is a graph, right? So it also
okay, so permuting two of the classes is also considered a symmetry. Yes.
Yes, permuting and also symmetries of the stochastic block model. And this is a semi-direct product you can show.
Yes. So the symmetry group will depend on the graph, right?
Yes.
Yes. So what algorithmic bias goes into there to choose the stochastic block model? I don't know if the question is well defined, but I hope you understand.
So, this is a good question because so first of all, you can just take out of the box clustering methods, but they don't really guarantee that the stochastic block model is going to approximate the graph in the sense of irregularity. So if you do that, then the theory only motivates the method, but it doesn't justify rigorously the method. There are methods to actually compute, there are algorithms to actually compute this Szemerédi partition. They're not efficient. And they don't work so well in practice. And this is actually something I actually work on now, how to derive algorithms that actually do work in practice. So there is some bias. The choice of clustering is going to give you a bias. But if you are able to guarantee that the stochastic block model gives small irregularity, then all of the symmetries of the stochastic block model, including the permutations within cluster, are going to perturb just a little bit the adjacency matrix. So in a sense, it doesn't matter, right? If then the method that you use is continuous, it doesn't matter what blocks you ended up with, in a sense. But it is Yes, it gives you a different bias depending on the block structure. It's sensitive to this.
Okay. More questions. Just speak up. Okay. Then I don't think there seem to be any questions from the audience. Then let's thank Ron again. And all of you watching on YouTube and here, we will be back in 3 weeks with another seminar.
Okay, thank you.